in the, so I guess I have do some things similar in the Gaussian animation. I count the number of corporations in the Gaussian animation, and it's around, let me see. So the Gaussian elimination, which part? I think it's this one. Okay, that's the things we want. So for the Gaussian elimination, I should write this one is wrong. It should be it's actually the big O. It should be the 2/3 in cubic, and this one it should be the big O 2/3 and cubic. If you go back to take a look at the lecture notes on the about the Gaussian animation, and then it should be 2/3 and cubic. Because if you have a very big number, the n cubic, and then actually the two it matters. And I will compare this methods, the LU factorization methods, to another methods later on. And that is the Choleski factorization methods. And now let's see, let's record some things very important theoretical results about the LU factorization. And this is general version. I mentioned this again because this is quite important. The LU factorization can be applied to the leading principles of matrix, to the matrix whose leading principles matrix, some matrices are all singular. This is the most general version. And for some particular cases, and then we have mentioned here, and then we also do some definition here. This is the special cases. The first special cases is strictly diagonal dominant, and then the second special cases is symmetric positive definite. And I have also mentioned how to combine the theorem and some other knowledge to derive the corollary result here. This is quite interesting, combine different theorem to get the corollary. And this is usually the math papers do such a things, and then so that you have a simple version to check whether a matrix is satisfied the condition, and then we can have the LU factorization. And also, I mentioned at the end of the class, last time, we can actually have a very general version, very general versions of the LU factorization, but this time is for any non-singular matrix A. So what we mentioned above is to directly do the LU factorization, and that is what we have for the theorem 9.1 and corollary 9.4. And this is, we are going to apply the LU factorization to the A directly. But for the more general cases, we are applying the LU factorizations for the permutations result. And this is the permutations matrix. And actually, so for examples, you are doing a lot of, you are going to do some row exchange in your Gaussian animation. You know what kind of row exchange you need, and then you can do the row exchange beforehand. And this is the pre-processing here. You do the row exchange here. And last time, I just briefly mentioned what does the permutations matrix looks like. And this time, I'm going to talk more about the permutations matrix. Let me see. So in case you cannot understand the permutation, and I'm going to mention more things about the permutation matrix here. So we have just one basics operation here. For example, you are doing the row exchange, row 2 and then row 3, and how to create the permutations row matrix. corresponding to this row exchange. So what you did is to, so first, let's say we are doing operation row exchange operations to, this is the row exchange. And then we are doing the row exchange for the matrix for 3 by 3 matrix. And then how can we create that row exchange matrix? We just have 1 1 1 0 0 0 0 0 0. This is the identity matrix. And if you want to do the row exchange, and then what you get is to exchange the row 2 and row 3 in the identity matrix. And this is your rotations matrix P. And let's see. So why do this can help us to get the row exchange here? So for example, this is A11, A12, A13, A21, A22, A23, A31, A32, and A33. And if you do the multiplications on the left-hand side, and what can you get? So for the first element, that is the first row, times the first column, and then that is just A11. And the first row times the second column, and then that is the A12. And the first row times the A13, the third column, and then that is the A13. And then now you should pay attention to this. I'm going to multiply the second row and the columns on the right hand side. This is the first column, and then the second row and first column, and that is the 2 1 positions here. And if you do the multiplication, and then you will find out that we only have the 1 at the third component, right? And then so if we do the multiplication, this one multiplied by this one at the values at this point as A31. And once again, for this column, for this component, it's just the second row and then times the second column. And you will see only this one is valid and then this one is valid in this multiplication, and the other are 0, right? So this one we got is A32. And the same things happens to the third column, the second row times the third column, and then that is the element here, and then we got A33. And you would do the same thing for the third row, and then the third row here times the first column, and then we got the A21, and then first the third row times the second column, and then we get A22 and then A23. And this is how we do the row exchange with the matrix multiplication. Can you see that? So the row exchange or the row combinations matrix is quite simple. You just need to switch the identity matrix, the corresponding rows in the identity matrix. And what is the P? The P here is that, so maybe you are expecting, so for example here, you are expecting you are going to do the row exchange, row 1 to the row 2, and then at the second round iteration, you are going to change the row 2 to the row 3. And what is this? You can actually do the row exchange here. Maybe first you can create the row 1, row 2 exchange. Row 1, row 2 exchange, and then this is the corresponding matrix here, 0 1. I guess it's not this one. The row 1, row 2. This is row 2. This is row 1, and then for this rotations matrix, and then for this rotation matrix, and then you will have the row 2, and then exchange to the row 3, and this is the one. So what you have
is, okay, this is, let's say this is a permutation at the first round. This is the permutations at the second round. And this is all the permutations you need to calculate for that Gaussian animation. So at the end of the day, your big P, the big permutation matrix should be P1 and then times P2. And this means that you are doing the permutations one by one to the matrix. So you do the permutation row 1, row 2 permutation first, and then apply the row 2, row 3 permutations to the result matrix. And this is how the permutations works. And after you do the permutations beforehand, and then you know that you don't need to do the row exchange anymore for the matrix during the Gaussian animation, so that you can apply the LU factorizations to the results matrix. Does that make sense? So this is just a rough idea about the general case, but you don't need to know about this for your final exam, or maybe homework, but not for final exam, because this is an advanced topic. And so this is all the things. And I also mentioned that this is based on the LU factorization is based on the Gaussian animation, and is the Gaussian animations operations, it needs 2/3 and cubic. And now we are going to create one algorithm that cut the operation, the number of operations to one half of this number. And how can we do that? And this is the so-called Choleski factorization. So we are expecting that this Choleski factorizations can cut down the cost of the computations into one half. And how can we do that? Actually, this one is going to making use of the symmetry of the matrix. So before this one, the LU factorization, and then what we are going to calculate. So I'm going to write down the LU factorization here first. And then for the LU factorization, if you remember it correct, and then this is the lower left matrix, and then this is the upper right matrix. And which means that you need to know the values here, and then you need to know the values here, right? And then it's around n squared element. You need to calculate n squared element here. So what happens to the Choleski factorization? And the idea is to factorize matrix A into, so this is the LU factorization, but for the Choleski factorization, you're going to factorize the matrix into B, and then the B transpose. And then what is the B here? B is a lower left triangular matrix. And as you can see here, we are going to use the symmetry, and then which means that this is the lower left, right? But because the B transpose is just the same thing as here, but we do the transpose, right? Each value here, we already know here, and then we just do some transpose here, and then actually that value, this one is the same as this one, and this one is the same as this one. So which means that we just need to know n squared divided by 2 value. Because you have, this is n by n matrix, and then so the elements here in total we have n. If we calculate how many entries here, it should be the n by n and then divided by 2. But here the upper right part is 0, all zeros. So, but for this matrix B, if we want to write down the matrix B, and then we just need to write down the values for the lower left part, and then the lower left part, it just contains n by n, that is n times n divided by 2 entries here. So that is, so here we have m by n entries, but here we just need to know m by n and then divide by 2 value components here. And I'm going to take a look at the theorem here. Actually, we cannot apply this Choleski factorization to any arbitrary matrix. There's some special requirement for the A matrix here. So I'm going to state the theorem about the Choleski factorizations, but I'm not going to prove it. If you are interested, once again, if you are interested in the proof, then you can go to the textbook. But we are going to take a look at the theorem that is proved by some very great. I think that mathematicians is just called Choleski. A lot of mathematicians just name their theorem or the algorithm by their name. It's like, this is my product. You should memorize me. And this is the Choleski factorization. So he found out that, okay, we can apply this Choleski factorizations in such a situation. So the A should be symmetric and positive definite. And you will see this is the second special case in the LU factorization, which means that for the positive definite matrix, you can either apply the LU factorization or you can apply the Choleski factorization. Definite matrix, and so this is the requirement, and this is so important. Actually, for every theorem in the mathematics, you should notice, you should put some attention to the assumption. A lot of time, my friends and then would play some joke with me, like, okay, I would give you some money, and then if there's the assumption, you know, and a lot of times that they said, let the assumptions hold, and then I would do something to do something. And this is some mathematics joke. There's the assumptions. And then let's say the assumptions hold. Okay, this is the assumption. And so every time you see a theorem in the mathematics, you should take a look at the assumption first. Otherwise, maybe you cannot do, you cannot have the conclusion. So this is the conclusions based on the assumption. And then there is a unique lower triangular matrix B. And then, there are some things with this. There's also some things about this matrix, this lower triangular matrix, and then it's actually with positive entries on the diagonal. With positive entries, I usually forget this things about the Choleski factorization, but it has the positive entries in its diagonal, and it's just one restrictions on the diagonal matrix, because you will see later on. Actually, it could be, if you do the calculation, it could be positive or negative, but we require that we put the restriction here and then make it to be positive. And the A can be factorized into B and then times the B transpose. And I'm going to highlight this part. We are going to require the restrict the entries on the diagonal to be positive. This is the things. Okay, so I'm going to show you one example. The calculation is not fun. And before I go to explain the whole idea, the general formulation, I just give you one simple example, and this is quite similar to what you have on your homework. And otherwise you would get sleepy. The derivation part is quite long. And this is the example. And I just say this is the lower left triangular matrix, and then with positive definite positive entries on the diagonal. And so there's one example. factorize determined the Choleski B transpose factorization. Actually, if you have in fact, if you have a matrix A, then you want to apply the Choleski factorization to this matrix, you might need to check if it is a positive definite matrix first, right? But here, the question tells you, actually, this one is the positive definite, and then we can skip this step. But if the question does not tell you this is a positive definite matrix, and then you might double check if this one is a positive definite matrix. But the question tells us that, okay, the question already know this is positive definite. And this is 3 to, oh, the number is quite weird. Don't mind this, it's quite weird. It's not the integer. So this is the A matrix. And we want to get the A equals to B transpose. And then what should we do? And then actually you are going to, okay, let's say the B matrix looks like this. And then because it's a lower left matrix, and then we are going to have B11. This is the 3 by 3 matrix. So the B is also 3 by 3. And then we have the B11, B21, B22, B31, B32, B33, 0, here. Okay. The rest of things is just some basics and length 3 calculation. And let's see. And A is just equals to, okay, I'm going to put the number here, the index here. A11, A12, A13. A21, A22, A23, A31, A32, A33. And what is this? And we are expecting this to be a Choleski factorization, and which means that we have, this is B matrix, and then we have the B transpose for the other component in the product. This is B transpose. Congratulations. Do I hit the recording? Yes, I hit the recording. Okay, thank you. Thank God. Thanks God. Okay, good. Let's see the B transpose. B11, B21. You know the transpose, right? Just flip the column and the rows. Okay. B11, B21, and then B31. And then this is the first column, and then it becomes the first row. And then the second column will become the second row. And then the last column will become the last row. And then this is the B transpose. And then the other things are just some boring calculation. Oh, God helps me do the calculation. And you can use the ChatGPT 4. You know that, right? The ChatGPT 4 has a better mathematics capability than the ChatGPT 3. And if you use a ChatGPT 4, oh, you know that you can take the video. And that is the big news. I love that one. And oh, you all know that there's demonstrations on the ChatGPT 4. Oh, the ChatGPT 4.0 can be the mathematics instructor. If you take the whole, the entire demonstration, and then it will tutor one high school student to do the mathematics problem. And that's so dramatic. A great things, I would just say just a great things. Maybe you don't need to learn mathematics anymore. Okay, let's calculate the component. The first component is just the B11 square. This is just the first row, and then the first column. And then the second element here is 1, 2, and then which means that we need the first row and the second column here. First row and the second column, do the multiplication, and then we got this B11 and then B21. And I'm going to do all the calculation here. let's say you already know this, or you can get it, you already get this one from ChatGPT. But nowadays, you cannot use the ChatGPT to do your exam. So you need to know how to do a calculation and B21 square. And hopefully there's one day, and then human or the mathematics professors know that there's no need to do the calculation anymore for the students. Okay, and this is the things. But actually, I believe that if you learn mathematics, and then your job cannot be replaced by the AI. This is my strong belief. If you go deeper, and then the AI cannot do the calculation or the proof. Okay, this is the calculation, all the numbers we have here. And what are you going to do is to compare the value you have. So what we have in the A matrix, the 4, and then we have this one at the 1, 1 position, right? Which means that the B11 square equals to 4. This is our first equation. And then our second equation is let's compare this value. You will see that this is quite symmetric. This matrix is quite symmetric. So what we are going to compare is just the upper right triangular. You don't need to compare this value anymore because they are symmetric, right? So we don't need to compare these 3 values here. Let's just compare the things above the diagonal and the diagonal. So the second one, and then you will see this. So what's this? So this is the -1. And then we get B11, B21 equals to -1. And let's see. And then we are going further, and then we got we have this B11 and then B31. And we got B11, B31, and then equals to 1. And next, what do we have? We have the things on the diagonal. And that is the B21, B22. And then I got this one. And I just compared the component at the same positions. I got the B21 square. B21 square, and then plus the B22 square, and then equals to 4.25. And I'm going to compare the next one. The next one, I'm going to use this color. And this is the 2.715, and then its corresponding B expressions is B21, B31, and then plus B22, B32, and then 2.75. And the next things I'm going to compare, that's the last items I have. And then that's the 3.5. And then the expressions at the bottom here. And then I got B31 square, and then B32 square, and then B33 square. You can see the calculation is pretty long. So if this is on your final exam, and then don't worry, it should be just a 3x3 matrix. It could not be a 4x4 matrix. It would be too horrible. I'm going to solve this. If you solve this 1 by 1, and then you will see the benefit. And don't forget that I'm going to require that the BII is a positive number. And you immediately see that why I'm going to require that the B11 or BII is positive, because it could be negative or positive. But in the factorization theorem, and then we restrict the BII number to be positive. So the B11 should be 2. And this one, it should be 2. B11, it should be 2. And you will see how lucky we are. We already know the B11 for the second expressions. So which means that it's so easy to solve for the B21. And then it's just the -1 divided by the B11. and then that's the -1 divided by 2, and then that is the -0.5. And once again, we know the B11, and it's so easy to solve for the B31. And that's the things, and then that is the 0.5. And what about this? The third equation, there's a fourth equation. The fourth equation, you already know something about this, and then there's just one unknown variable here. Actually, we already know the B21 from the second equation, so this one is already a no, something we already know here, which means that we just need to solve for the B22 and doing the square root, and 4.25 divided minus B21 square, and then doing a square root, and if you do the calculation, and this one equals to 2, and if you take a look at the fifth equation, and then we are going to solve for the, actually you would see this. If we solve this first equation, we solve for B11. This is B21, and this is the B31. This is the corresponding positions there. And so for this equation, this position is 3,2. So we are going to solve for the B32, and then let's see the other values. B21 we know from here, and B31 we know from here, and then B22 we know it from here. So all these values we solve it before this equation, and then we already know the values. And then we just need to substitute all the values here. This is something we already know from the previous equation. And then we have B32 equals to 275 minus the B21, B31, and then divided by the B22. And this is the equation. And we have, actually, we have the B32 equals to 1.5. And now let's go to the last equation. We are going to solve for the B33. The corresponding position there is the 3,3 position. So B31 we already know from here. B32 we already know from here. So what's that? This is okay. This is B32. This is not B31. This is B32. My writing is so bad. Okay. We have B33, and then 3.5 minus the B31 square minus the B32 square, and doing the square root. And now you would get to the answer. This one, the B33 is 1. So which means that you have the B matrix now. The B matrix is 2, B11 as 2, and then B21 as -0.5, and then the B31 is 0.5, and then the B22 is 2, B32 is 1.5, and then the B33 is 1, and the other entries are 0. And we finished the Choleski factorizations for this 3x3 matrix. Does that make sense? So one thing I want to point out that, so you need to create a matrix in this direction. So first you create the matrix, the equations for this one, and then go from this direction. And then for the second row, you go from this direction and this one. You cannot create you can see we solve this equation sequentially, and then we know the value, some values before the next equations. So if you write the equation in this order, you write it. This is the first equation, and then you solve this is the second equation, it goes to this equation, and maybe you will have something missing here if you go into this direction. Let me see. Actually, it doesn't matter, but you cannot write it randomly. But you should follow this direction, or you should go from here, here, here. Otherwise, you would get the order wrong, and then you would find something unknown in this equation, and then you have to solve for 2 unknown variables for 1 equation, and that's not doable.
So you can follow either this direction to write down all the equation, or follow this direction to write down all the equations here.
And this is the things. And so I'm going to show you some things very quick. Let's see. What I'm going to show you is the general Choleski factorizations algorithm. And so for the general matrix, actually we can write, if this is an n by n matrix, and then we can keep creating the larger B and then larger B matrix, and then there would be n by n matrix, and then with the lower left non-zeros, it could be non-zeros element here in the lower left part, and then all the upper right triangular parts are 0. So if this is the n by n matrix, and then you will have a bigger matrix B, you could have a bigger matrix A as well, and then you would do some similar calculation here, and then to compare the value B11 and the A11, and then compare the B11, B21 with the A12, and then you solve for the B11 and then B21 and B31 and 1 by 1. The idea is the same. Does it make sense? But now we have the general algorithm for this. This is a general algorithm. That is by if you have a bigger matrix A and then n by n, and then you have a bigger matrix B and then n by n, and then what is the formula for the B element? And this is the Choleski factorization algorithm. And I'm going to mention this, but you don't know the general algorithm at the end of the day. You don't need to memorize this. And I just mentioned this because I want to compare this with the LU factorization. So what are you going to do is this is a bigger for loop. And then for this for loop, you are doing you're doing the following things. We are going to compute the, you will see we are compute the element here. So in this direction now, we are going to calculate the first column and the second column element and the third column element here. So for each iteration, I'm going to compute the corresponding column element, column I of the B matrix for each iteration. So for this bigger this for loop iteration, and then for each I, and then what's the BII? BII is just, so what we know is just the AII and something we calculate before this iteration, and AII, and then minus the sigma sum I minus 1 and K equals to 1, and then BIK squared. And the BIK value, the K is from 1 to I minus 1, and which means that for this order of the equation, and then we already know the value for the BIK. Does it make sense? So this is something we already know from the previous solving process, for the solving equations process. And this is the first things for each iteration. And I'm going to use one line to divide all these iteration here. So this is the first iteration 1. You will see in the iteration 1, and this is the iteration 1, and then for each iteration, and then you will see what we did is to solve for this is iteration 2. And for each iteration, we will first solve for the BII. So this is what we did here, solve for the BII. And then the third step is another for loop. once we get the number BII, and then we will solve for the rest of the elements in this column, and then the rest of the elements in this column is from the I plus 1 and then to the n. And then we would do such a calculation here. And then what's the BJI? BJI equals to AIJ and then minus, this is some numbers we already know from the previous iteration, BIK, BJK. You will see the K is just smaller than or equals to I minus 1. And this is some value we already know from the previous iteration. And then divided by the BII. BII is just numbers we just calculate from this big iteration I, the big iteration I. And so after you get all the column value, column I value, and then we will end this for loop. And we also would end the bigger for loop here. And then we will end the big iterations here if you do all the iteration for the I index. So I have written down all this algorithm here, and I'm going to tell you, but you can also count the number of the operations we need here. So for this algorithm, you will see, actually for this algorithm, we need how many multiplication on. So for this one, we have multiplication or divisions, and the number of the multiplication and divisions we need for this Choleski factorization is 616 n cubic, and then plus 1 square, 1/2 of square n square, and then minus 2/3 n. And for the additions and subtractions we need is the 1/6 n cubic and then minus 1/6 n. You can count it one by one. So I have to tell you how to, I have to show you how to count the number of the three operations we need before this one. You can do the same thing for this algorithm, and then you will, at the end of the day, you find out the number of the multiplication divisions we need, and then the number of the operations, the number of addition and subtractions we need for this calculation. So approximately the total number of the operations we need is just 1/3, 1/3 n cubic. And this is all weird compared to what we have for the Gaussian elimination. This is 2/3 n cubic, and then we cut down the cost of the calculations into 1/2. And this is because at the very beginning of in this class, I just mentioned this. Because the area factorization, you need to know n by n values, n times n values, and then but for the Choleski factorizations, we just need the n by n and then divided by 2 values. And then this is why we cut down the computational cost into 1/2. And this is all the things we have today. But I want to put a remark to this before you leave. Actually, this number of the operations, the saving of the cost is a little bit confusing because there's a square root here, and then a lot of time you take a lot of time to in the computer. It takes much time to do the square root. So people come up with some modified version of the Choleski factorization to save the computational cost as well. You can take a look at the textbook for the advanced topic, and then I'll just mention this if you are interested how to save the computational cost to do the square root. And this is all the things. And then if you have questions, you can come over to ask me.